yesterday we did diffraction, and we shifted things a little bit differently. Talked about diffraction first, and then imaging. I was trying something different. Sometimes it's better to do one versus the other. Let's see how today goes. All right. You had a lot of the references that I gave you already yesterday. You've already got those. There's a lot of good books out there, and there's even more now. Some of the classic books, as well as some of the newer books. All right. What I'd like to talk about today is imaging per se. And in imaging, we talk about 3 different modes: amplitude contrast, diffraction contrast, and phase contrast. Amplitude contrast is usually a low magnification image. Diffraction contrast is when we're trying to look at defects. Phase contrast is when we're doing high resolution imaging. So we'll go to all 3 of those modes. We already talked about the microscope per se. We really don't do a lot of work in the illumination system now. We try to get in TEM imaging mainly a parallel beam. The objective lens is fixed, and contrast is now how we orient the sample relative to everything else. So we'll mainly be working with either an under-focused beam or a parallel beam for TEM imaging. And we talked about this yesterday, excuse me. When we're in imaging mode, the post-specimen lenses are looking not at the back focal plane, but they're looking at the image plane. So when we talk about magnification changes, we're changing the projector lenses. And remember, there's multiple lenses that give us magnification. All right. What are the major factors that control contrast? That's what we have to think about here. And there's 4 in my mind. First thing, it's all scattering from the sample. So the beam's coming in, scattering. I'm going to have problems today. Scattering. The first type of contrast is thickness contrast. Okay? Different thickness areas of the sample stop the beam from coming through. So you either get lighter areas or darker areas. Pretty simple. The second type of contrast is atomic number contrast. We talked a little bit about that in diffraction when we go high Z materials scatter more than low Z materials. So you'll get basically darker versus lighter. Okay? Orientation contrast is diffraction contrast, and we'll be talking a bit more about that. And again, Hamish will also be talking about that and how we interpret it. And then when we look at defects, it's a combination of diffraction and scattering contrast to get the image to analyze it. All right. So most of the things we'll be talking about today are elastic contrast. So we're in elastic contrast is either the amplitude contrast or the diffraction contrast. We're not looking at inelastic scattering. That's this afternoon. Okay? All of these are considered elastic processes. Okay, so let's look at mass contrast first. Mass contrast comes to the fact that different atomic number materials or different thickness materials attenuate the beam that's coming straight through the sample at different amounts. You can think of it very simply. If you got a huge dense particle, the electrons aren't going to penetrate it, or they're scattered off in wide angles so the beam is not coming straight through. That's simple mass contrast. Diffraction contrast is mainly due to the electron beam coming in and being diffracted away. We'll see how that works in a little bit. Phase contrast is a third thing, and it's an interference phenomenon, and we'll do that too. So again, we're not going to be talking about diffraction. We're going to be talking mainly about imaging. And a lot of the contrast is involving the insertion or removal of apertures. And those apertures are actually put in the back focal plane, okay? Because they define which beams come through and assist in creating contrast. So let's first look at elastic scattering in an amorphous solid. We talked about this equation yesterday for diffraction, okay? And we said that we've got the atomic structure factor times some sort of periodicity, which is related to the nearest neighbor distances in the material, okay? So when we plot this function out, we get a function that looks something like this. We got intensity versus scattering angle, and in an amorphous solid, we have this periodic undulation, okay? Now, how do we get contrast? Remember, I made the point yesterday. We know a sample is in focus when there is no contrast. Why? Because when the beam hits a sample, it scatters through. If we collect all those scattered electrons back to the image, if we collect everything that went in, we should have nothing. The way we get contrast in this is by restricting the information that comes straight through. And that can be done several ways. The easiest way is by inserting an aperture and just saying, I want just these electrons. I don't want to have any of these. Okay? That gives rise to contrast as we see here. Okay? What's happening here is this is a biological material. It's been stained with high atomic numbers. Okay? Because it's stained with a high atomic number, the scattering factor for those high atomic numbers is larger and at larger angles. So the information that's scattered here doesn't come straight through, but it's off at an angle. Okay? This is a lower atomic number. The information is scattered off at an angle, but because it's a lower atomic number, it's scattered at a different angle. Okay? So if we put in an aperture here, different size apertures, we'll be able to say the very high dark areas are from high angle scattering, and we block that out. The lighter areas are from lower angle scattering, and we get that through. Simple mass contrast, but the mass contrast is due to the change in the intensity distribution with angle. Okay? Did I go the right way? Mass thickness contrast is the most important for biological or organic samples generally. Okay? It's very good for non-crystalline materials. You can, I just described why high Z materials scatter more electrons than low Z materials. They're off at a bigger angle. By using an aperture to block them out, we see contrast. The same thing happens when the sample thickness increases. Can have uniform material, thicker samples means the scattered electrons are further out. Again, we can block them out with an aperture and we get contrast. Okay? So when we talk of a bright field image, what I'm talking about is an image of the electrons that go straight through the sample. And the bright field image is formed by just those that go straight through. It's called bright field because if I look in a hole, it's bright. Okay? Okay. Amplitude contrast, okay, is formed, like I said, by the beam coming in, interacting with the sample, and going straight through. Okay? So we have our sample. We can describe that as a simple, the intensity is the wave function coming out times its complex conjugate. And you can write that out mathematically. I'm not going to bother to do it here, but it's simply the intensity that comes in e to a interaction coefficient times the thickness. Okay? The way we get contrast is some of these, if we collect all the electrons, this will be equal to all of that. What we do is, in the back focal plane of the pattern, we put in an aperture. So the electrons that are scattered at higher angles are blocked out, and we just have the intensity coming straight through. So it's a simple, in an amorphous solid or non-crystalline solid, it's an exponential in thickness. Okay? Here's an example of mass thickness contrast. It's a stained biological material. This is actually a piece of my beard. So we did a cross section It's the core of the hair, of the hair in my beard. This is not me. This is a mouse. But what we're seeing here is we've stained it. We've got high atomic number in certain areas, low atomic numbers elsewhere. Okay, the thicker or higher atomic numbers are darker than the lighter areas, and you also see very discrete holes, so the beam's going straight through. This is a mouse muscle. Okay, again, it's been stained, so different structures take up the stain differently, and we can differentiate between them by in this case, the atomic number contrast. This area is roughly constant in thickness. It's microtomed. This was microtomed too, but my hair is very brittle. I'll give you another example of mass thickness contrast, this time in a semiconductor device. Okay, this happens to be amplitude contrast. It's a relatively thick semiconductor, but it consists of electrical contacts. So we got silicon, we got tungsten, silicon and copper. Okay, and in this area, they're running current through the device. We got a void formed. Okay, so the void formed, and what's a void? It's a hole, it's thinner. So here we have our copper via, and we've got a lighter area because it's thinner. Okay? So simple mass contrast, thickness contrast. Now, phase contrast is slightly different. We still have a beam coming into the sample, interacts with the sample, and the beam comes out. So we still have that same basic equation. But what's happening now is in phase contrast, instead of just looking at the direct beam, we let as much information come as possible. What's happening there? Remember the description we had of the Young's fringe experiment, where we had interference of beams. Well, in phase contrast, it's really an interference of the primary beam and any scattered electrons that come in. Now, this particular example assumes crystalline material, but it doesn't matter. What happens is we get the intensity psi star, and so you can expand that, and if it's a non-crystalline material, we have the first two terms, which we saw previously, but now there's additional terms. Okay? So what we're getting now in the image is not just what comes through, which is that guy, but an interference of multiple terms. That interference gives rise to contrast. Okay, let me give you an example of that. This is a non-crystalline sample. If I put in an aperture and only look at the transmitted beam, that'll mainly be amplitude contrast. If I open the aperture up and allow interference to happen, we'll get additional contrast, and we'll see that here. This is, admittedly, doesn't look very good from here. Maybe if I look further back. There's very little contrast there. Okay? It's an amplitude contrast image. There's not a lot there. Why? The sample is carbon, and more carbon, and a little bit of oxygen here. So not a lot of contrast. If we remove that aperture, now we start to pick up contrast because we got an interference phenomenon going on. Okay? How can we increase that contrast? We can increase the contrast, back up a slide, by looking at these terms and saying, I want to increase the contrast, so I want to increase the contribution of the additional terms. What I haven't shown you, because I haven't expanded this out, is part of the terms in here have to do with the phase shift of the individual diffracted beams. Okay? Electrons from coming straight through have one phase. Electrons coming off at an angle have a different phase. We can increase that phase shift, and hence the contribution here, by doing something very simple. Defocus the microscope slightly. When you defocus the microscope, you introduce a phase shift between the direct through beam and a beam that's off at an angle. Why? Aberrations. Changing the defocus changes the phase, and that's one of the terms in the aberrations. Okay? So now, here's the same area of the sample for different values of defocus. What do we see? The contrast for very little defocus is weak. As we increase the defocus, the contrast is increasing. Okay? So everybody says, well, let's just work with a defocused image. The problem is, as you defocus the image, we also lose resolution due to, remember we talked about Fresnel diffraction yesterday. Fresnel diffraction is a phase shift, it's a phase contrast. As the defocus increases, so does the Fresnel diffraction. That is what you're actually seeing here, is Fresnel diffraction around the edges of the particles. Your eye likes this because there's more contrast, but it's also defocused. The resolution in this image is actually worse than the resolution in that image. Okay, I'll give you another example of that. This is a polymer. Same area of the polymer. What did I tell you yesterday? Minimum contrast is focus. As we go larger defocus, the contrast increases, either negative or positive. Also, I want you to look at this. That's the same area of the sample. We can go negative defocus or positive defocus. The contrast changes. That's important in TEM, in conventional TEM imaging. Positive and negative contrast change, positive and negative defocus changes the contrast. You will see that in TEM. In a little bit, you'll say you won't see that in STEM because it's a different mechanism. All right, the other type of contrast, and Hamish is going to talk more about how we analyze this, is diffraction contrast. Okay. Now, how do we get diffraction contrast? Here's a perfect crystal of the sample. Here's a perfect crystal of the sample. There's a grain boundary going there. This area is dark. This area is light. There's a hole. Okay, everything, it's white because it's a hole because the beam's going straight through. In this area of the crystal is oriented such that there is not a lot of electrons that are diffracted off to an angle. So most of the electrons are going straight through. And there is an aperture, I don't show it, but there's an aperture just looking at the bright field beam. Now, in this area, what's happening is the electrons are being diffracted off at an angle. So not all the electrons are going straight through, but a lot of them are going into a diffracted beam. If I have an aperture in there, what happens? Those electrons are stopped, so they don't contribute to an image. The area is dark. So in diffraction contrast, we have alternating areas of light and dark, which we can control by adjusting the diffracting conditions, by adjusting the amount of intensity that's either going straight through or being diffracted off. Okay? That's a big crystal. Here's a dislocation. Okay? Again, a similar principle. This area, most of the electrons are going through. In this area, because of the bending of the planes, we have a diffraction effect, and the area is dark because the electrons that are going there are Bragg diffracted out somewhere else, and an aperture is stopping them from getting back. If there was no aperture, you'd have no contrast. I'm not going to talk about the mathematics of this. I'll leave that to Hamish. But the interpretation of image contrast really can be done. It's more than a 60-minute lecture just on that. But basically, we take the Schrodinger equation. We talk about what the material is made of. We know we've got a wave function coming in. We want to analyze the wave function coming out. And what happens is, as the beam goes through the solid, it goes through an atomic potential. That atomic potential is a function of what's ever in the solid, either it's amorphous, whether it's crystalline, or whether there's a defect. We can model that atomic potential, model the defect, model the crystal structure, put that into the Schrodinger equation, and solve it. The intensity that comes out then is psi star, the wave function that leaves the sample. The other, what is the red dot for? Okay, the other thing that we had is we mentioned that mainly we're in TEM, we do a lot of bright field work. So we're looking at a beam coming straight through. Bright field, we know it's a bright field because when there's a hole in the sample, it's just bright. When we get onto the sample, we get a diffraction effect. It gets dark. A dark field image is just the opposite. We're looking, instead of at the image that comes straight through, we go to the outside and look at the diffracted beams. So now the sample is white and the hole is dark. So when I talk about bright field and dark field, I mean, one, we're looking at a beam coming straight through, one, we're looking at diffracted beams. Now, bright field and dark field imaging are actually fairly simple. We have an aperture that it's called the objective aperture. It's in the back focal plane of the diffraction pattern. We let the beam come straight through. When we want a bright field image, we use an objective aperture to block out all the diffracted beams and just put an aperture around the central beam. That gives us our bright field image. How would we make a dark field image? Well, the naive way of doing it is, okay, I'm just going to move my aperture off to the side. And now I should get an image of just the areas of the crystal that contributed to that diffraction spot. Does that work? The answer is yes. However, remember what we talked about yesterday in terms of aberrations. The aberrations of any lens increase as we go to a higher angle away from the straight through beam. So if you wanted a higher resolution image, you don't want to do an off-axis dark field. What you'd rather have is have that beam come straight here. We do that by tilting the illumination. Remember we talked about the deflection coils. We can either translate the beam or tilt the beam. By tilting the beam, what we can do is we can move, if we want this diffracted beam in, we can tilt the beam one way or the other using the tilt coils and get that diffracted beam right down the optic axis and then form an image. That's a better way of doing dark field imaging. It's called tilted beam dark field, okay? And here's just an example of that. So there's off-axis dark field and on-axis dark field. You can do this. This is the better way to do it, okay? What happens when you do a bright field image? Here's a bright field image using that straight through beam of some defects in the material. This is a gamma prime system in nickel aluminum. Okay, if instead I tilt the beam so that that very weak reflection is now centered and form a dark field image, okay, we have a high resolution image of whatever phase is causing that particular reflection, okay? And in this case, you see what we have is gamma prime precipitates at the grain boundary and small gamma prime precipitates in the matrix. And we also have a dislocation here, which is coated with gamma prime. Okay, I'm going to skip this. We talked about this before. And we talked about how we do the tilting via deflection coils. Oops. What happened there? Okay. The other thing that we can do is do diffraction contrast, and I mentioned this earlier again. We saw this image before. The way we form that image is we have a bright field beam, a diffracted beam coming in, put an objective aperture in, and just form the bright field. This is dark because the diffracted beam's being blocked. Okay. Same thing happens in an image of a dislocation. In this part, we have a perfect crystal. In this area where the dislocation is, the crystalline planes are being bent. And when the beam comes down at a certain point, at a certain angle, we meet the Bragg diffracting conditions. So those scattered electrons are off at an angle. If we put an aperture to block those out, what's going to happen? We'll have a bright area where it's not at the Bragg angle, and we'll have a dark angle where it's at the Bragg angle. There are a lot of other phenomena that happen due to crystalline materials. There are phenomena called bend contours and thickness fringes. Hamish, are you going to talk about bend contours and thickness fringes? I don't remember.
Not really.
Not really? Okay. I'll just go.
Just a little bit.
Okay, I'll just go briefly. It won't hurt you to see it twice. Kinematical theory, I'm not going to talk about. We'll just skip it through. What's a thickness fringe? If we have a crystalline material, we can say that the intensity should come through, and I didn't derive this equation. The intensity in a crystalline material will vary sinusoidally with the thickness of the solid. Okay, so we'd expect a sinusoidal variation of the intensity. We see the sinusoidal variation. Okay, we can literally count the number of fringes that periodicity is related to something called the extinction distance in the solid. Okay. Ideally, we'd expect it to oscillate back and forth. In reality, it oscillates, but gets weaker and weaker. That's due to diffraction, anomalous diffraction in the solid. All right, so here's an example. This is an amorphous material. This is silicon, and we're going thicker and thicker. We can see nice thickness fringes, because if I know the extinction distance, I can tell you how thick each of these areas are. And as we get very thick, they just decay away. Okay. Typical extinction distance, you can look up in the good books or calculate it. Okay, so just to give you a sense, at 100 kilovolts, extinction distances depend on atomic number. Right, the higher the atomic number, the faster the beam oscillates down or gets degraded, and also the higher the scattering vector. These are the different reflections. Okay. And they all vary free between FCC, BCC, or HCP. They're all variable. Okay. Bend contours are another diffraction phenomenon. Okay. A bend contour looks exactly like I've shown you here. How do you know it's a bend contour? It's very easy to tell in a microscope. Just tilt the sample a little bit. These things move all over the place. And we'll see that later probably. Okay. Where's a bend contour comes from? A bend contour comes from that same equation that gave us a thickness fringe. But instead of varying the thickness, I'm going to vary the orientation of the crystal. So we've got pi times the thickness times the orientation. Okay. Now let's pretend we have a uniformly thick sample and it's slightly bent. What's going to happen is the thickness is constant, but we're getting a gradual change in orientation. So what are we doing? We're getting either Bragg diffraction or no Bragg diffraction. And we see that very nicely here. Okay. These are very easy to recognize. Usually, if you're right at a zone, we almost see that. You'll see the symmetry of the zone that you see here. If I took a diffraction pattern right from the center of that bend contour, we got a nice symmetric, that's a 110 type pattern. Here's another one, 112. Where are we here? I can't see, I'm too close to it. But you notice each one of these contours corresponds to a specific reflection. G2 is that one. So we can see something about the crystalline solid. It's important to recognize them. I actually use these, if you have a lot of bend contours, you know your sample's distorted. If you have only a few, it's easy, it helps you get close to an orientation, because you don't have to go back and forth between an image and a diffraction pattern. And I've already mentioned that these thickness fringes, sorry, I'm having, die out. So theoretically, they're uniform with thickness, but in reality, they die out, and they die out because of the effective S is decreasing. So they oscillate. It's called anomalous absorption. The other thing that you can get is you can get a uniform sample, uniformly thick sample, but an area of the sample can be shifted due to a stacking fault. So there's an example of a stacking fault. You see a small shift in the planes at that point where the fault is. The kind of contrast you get from a stacking fault looks something like this. Okay, I'm not going to talk about that contrast right now. It's just will be on what I want to talk about today. Okay, but stacking fault contrast can be analyzed. We can determine the nature of the dislocations bounding that stacking fault. We can also tell something about the thickness of the sample by the number of fringes. Let's skip that. Actually, and so I'm going to skip most of the stuff on diffraction contrast, because that's some of the material that Hamish is going to talk about. I mentioned diffraction contrast, and I bring up just a couple of examples just to show you. This is a subgrain boundary in a material. Why are we interested in subgrain boundaries? Well, we really want to know the nature of the dislocations forming up that same subgrain boundary. And the way you do that is by doing a diffraction analysis, very, very carefully controlling the orientation of the crystal, noting when a dislocation is in contrast or out of contrast where it's invisible. The next example shows you that. Nope, let me just find it. There we go. Okay. Again, a very old image. Okay. This is the same dislocation network. What I'm able to do is by noting when the dislocation is in contrast, that is dark, or out of contrast. Here, I can determine the nature of the Burgers vector of that contrast by noting when I have it's either in contrast or out of contrast. And I think that's some of the stuff you're going to talk about, right? Okay. So I won't spend any more time about it, but just an example. Now, this is a systematic study. Remember we talked about yesterday how the Kikuchi patterns let us go between different areas of the crystal. Okay. Well, I did that in this particular sample. I think, is that the next slide? No, it isn't. I tilted the crystal. I used the Kikuchi patterns. I found this area. I'd orient the crystal in this case. I'd orient near 001, okay, 001 axis. And I would orient a diffracting vector. So the 110 diffracting vector was strong. I'd get a certain contrast. Then the same zone axis tilted a little bit differently. So the 200 was right. Notice the contrast changes. Okay, that dislocation is in contrast there. It's out of contrast there. If it's out of contrast, these particular planes are not in the Bragg reflecting condition. Okay, and by noting when they're in and out of contrast, you can make yourself a little table and figure out what the nature of that Burgers vector is. And again, Hamish is going to talk about that, so I'm going to skip this. Yes. And so remember, I showed you this yesterday. What we just did is we used the Kikuchi lines to orient the crystal and then just get different Bragg reflections. Very, very well excited. I'm going to skip all of this. The same thing holds not only for dislocations, but dislocation loops. We won't be talking much about that now because we don't have time for it today. All right. I'm going to leave that brief introduction to diffraction contrast and shift to phase contrast. And the reason I want to do that is the instrument you have here has an aberration corrector, and it will get you relatively high image resolution. And what I'd like to go over for a few minutes is how to look at phase contrast or high resolution images. It's always, everybody says, oh, I just want a high resolution, atomic resolution image. And they really don't think too much about it. So Hamish is going to talk about diffraction contrast and defects. I'm going to spend a little bit more time here on phase contrast. And remember, in phase contrast, what we do is we look at the scattering of all the electrons that come through the sample. Okay, so in general, we will not have an aperture. We will remove the aperture or put a very large aperture in. Okay. All right, so in diffraction contrast or amplitude contrast, again, we have a very small aperture, and we either look at the transmitted beam or one of the diffracted beams. In phase contrast, we have a very large aperture or no aperture at all. What happens in phase contrast is we have an interference phenomenon between the transmitted beam and each of the diffracted beams. That interference contrast gives rise to oscillations in the images. Okay. So here is an example of interference contrast. It's called a lattice image, but it's just an interference contrast between two beams coming through the solid. So we got a transmitted beam and one diffracted beam. And actually, the aperture, there's no aperture here. It was just two beams in a solid. We get an interference pattern. It's just like the Young's fringe experiment that we talked about earlier. Okay? These lines reflect the periodicity of the two beams that's interfering. Okay? They reflect that periodicity, and that periodicity happens to be due to the atomic structure of silicon because it's crystalline. Okay? Knowing which diffracted beams come in, knowing their spacing, we can work out what the spacing this is. It's also, because we know it's silicon, we can also use it to calibrate. This happens to be the 111 planes of silicon with roughly a 3 angstrom spacing. Okay. Now, there are several ways of forming a lattice image, which is a phase contrast. It's an interference image. You can form it by having two beams coming in, and instead of having one set, you would offset them so they're symmetric relative to the center. Again, that negates aberrations a little bit because one beam and the other beam are equally opposite, and so we get a better high resolution image. We can have a 3-beam condition where we got the main beam and two beams oscillating, or we can have one where we got multiple beams coming in. Now, think about this. If we only have two beams coming in, what are we going to do? We're going to get lines. If we, again, 3 beams, again, they're all interfering. We're going to get lines. What happens when you have multiple beams? Well, this is going to interfere with this. It's going to interfere with this. We're going to get a structured image. Okay? So here's an example of a phase contrast, high resolution image of pure silicon. And now I'm letting in all these beams come in. Okay? So I've oriented the crystal. We're getting an interference pattern in all directions. Each of these beams interfering with each other. Okay? We can measure the spacing in each of these directions. This happened to be 110 silicon. So we can derive whatever these interatomic placings are, and we go from 3 to 2 to roughly 1.5 angstroms. Okay. Now, I showed you this image earlier when we talked about instruments, because once we have an image like this, we've calibrated, we know the spacing, we can calibrate the magnification of the instrument. All right. Now, that's all fine and dandy. I showed you a perfect sample, uniformly thick. I gave you a beautiful high-resolution image. Wow. Is that the real world? The answer is normally no. The real world is a sample that doesn't look like this happens to be gold, relatively uniform right up to the very edge, and there's a hole. That's a good sample. Are most of the samples you're going to get like that? No. Most of the samples you're going to get look something like this. It's variable in thickness, there's variable orientation, and there may be amorphous material as well as a hole around it. Now you compare that image to that image, okay? That one looks nice and pretty. That's a nice publication image. That's the real world. Okay. What's going on here? What's going on here is we're getting phase contrast interference, but this area of the sample is multiple grains. So the grain here, although it's a small grain, it's a grain, are interfering in one orientation. This guy's a little different. These guys are even different again. There's defects in the material, and there's also a variation of thickness across this. Also, look at the very edge. It's very different. What's going on there? What's going on there is that we have a variation. I'll just zoom in right on the edge. We're going to look, we get a variation in thickness across the sample. So here's vacuum. Here's the very edge of the sample, the very thinnest part. We're getting a nice periodic image that looks beautiful. Okay? What's this stuff on the edge? That's amorphous grunge that's on the edge of the sample. It could be dirt. It could be just amorphous material. It could be carbon. What is it? We'll have to figure that out later. Now, what's happening here? I've got a nice, beautiful lattice image here, but all of a sudden the lattice image is getting corrupted. Doesn't look very good anymore. What's happening? What's happening is we're changing the thickness of the sample. We're going from a thin sample to a thicker sample to a thicker sample. Okay? And what we're doing is we're getting channeling and interference from different number of planes. Okay? And what we can see is there's a change in how those electrons can penetrate through the solid, and they begin to interfere. And we see that happening as a function of thickness. Can we control that? Not if your sample thickness is varying. Not if the orientation is varying. Okay? So one of the keys to doing good high-resolution imaging is making sure you know what's happening to your sample itself. Let's see what the next slide is. Yes, okay, so this happened. Here's that a little bit even better. So this is silicon. It's variable thickness. There's vacuum out here. There's a little bit of amorphous material out here. And we can see in this area, it's one thickness, and then there's an abrupt change. And notice how we go from white images to all of a sudden they go black. Let me go back the slide. Oop, wrong one. Okay. What's happening is we're going from white to black. As the electrons are going through, they're channeling and they're diffracting, they're interfering, and we're getting changes in not only the intensity, but also the contrast. So that's a big problem with high-resolution TEM imaging. As a function of thickness, as a function of focus, we can get white atoms or black atoms. That's always been the criticism of whenever somebody would come up to me and ask me, well, show me an image of an atom. I said, well, what color you want it. Do you want it white or dark? It depends on the focus. It depends on the thickness of the sample. Okay, here's another classic example. This is a strontium titanate, lithium manganate sample, okay? If I look at that image, that's a very complex image. Can I straightforwardly interpret that image? Can I say, well, there's an atom there, and, oh, wait a minute, there's an atom there, but wait a minute, what happened here? The atoms are changing. They're not round anymore. They're sort of strange in figure. And I come across here and go, what's going on? What's going on is we got a combination of sample thickness change, sample orientation change, and structure change. All of that's complicating this image. Here's another example of it. This is a nice, clean sample. Notice at the very edge, there's almost no amorphous material. This is more typical. You're almost always going to get a little bit of amorphous material. It could be damage, it could be carbon on the edge of your sample. Okay. And what are we seeing here? We got a nice clean sample where there's nothing on the edge. Almost all of your samples will look something like that rather than that. Getting a good clean image is always difficult. Phase contrast, this interference phenomena, changes with both thickness of the sample, I showed you two examples, but also with the focus. So in this case, we're going from a sample at one focus, and I'm looking at the change with thickness. Okay, now here's the same area, same thickness, but all I've done is change the focus. Okay. What's happened to the contrast? Notice these white atoms have now become dark. Okay, so looking through a high-resolution image, just looking at the image, can you interpret it directly? The answer is no. What I'm going to tell you need to do is you need to do a calculation. Again, we're not going to have time to talk about how to do those calculations. I'll recommend this particular computer program. It's GEMS by Pierre Stadelman. He's written a very nice suite of programs for educational purposes. You can get a free copy, but it's also pretty cheap to buy. He's now retired and he just writes the programs and does them. Very good program. What he does is he will divide the sample up. He'll ask the questions. I'll ask you, what's the material? What's the structure? He has a model that he puts in it, and he will calculate how the image goes through, how the waves travel through the crystal, and give you an image of what's coming out the projected potential. Okay, so he will have a model of a sample. From the model of the sample that you tell it what you got, he will calculate the atomic potentials, and from the atomic potentials and the operating conditions of the microscope, he'll get a projected wave function, and from the projected wave function, he'll produce an image. Now, and the other important thing that he does in this program is not only does he do this calculation, and that calculation is great, it's up to this point. The beam comes in, the beam comes out. The important thing is, remember we talked about the contrast transfer function of lenses. So in his modeling program, he includes all of the aberrations of the microscope. So you tell him the conditions, you tell the program the conditions of the microscope, wavelength, aberration coefficients, whatever, and he'll put all of that information into the calculation and produce now not a wave function that leaves a sample, but actually the transmitted wave function that you measure, which is modified by the contrast transfer function of the microscope. Okay? All of these things are included in his calculation. The change in focus, the variation of spherical aberration coefficient, that's all in the contrast transfer function. He'll add chromatic aberrations, spatial coherence, and he comes up with a total system function. Okay? It's a very good program. I highly recommend it. Okay? I'm going to skip this. Why is it important? Because in his program, he will, once you tell it the model material, he will generate a series of images as a function of thickness and as a function of defocus. Now you can go to your image and say, here's my model. Here's the thickness that I think it is. Does it match any of these? And you see, this is all the same sample. The only variation here is what's happening to the image as a function of thickness or as we defocus the sample, or defocus the lens. Okay. Okay, I'm going to skip this. I'm going to skip this. Oh, yes. Almost always, when you do a high-resolution TEM image, you're going to see nice fringes and something. Okay? Now, I want you to look very closely at that image. We got beautiful fringes, we got a high-resolution image, and all of a sudden the fringes are coming out here, and they're out in vacuum. How do I get that? How do I get a fringe in vacuum when there's no sample there? The problem is the aberrations of the microscope cause a phenomenon called delocalization. Okay, and the shift of the interference from the actual sample has to do with the aberrations of the microscope. In an aberration-corrected microscope like you have here, this delocalization can be minimized and actually made almost zero. Okay, so the good thing about an image aberration corrector, not only does it give you high-resolution imaging, by minimizing the aberrations from the defocus and spherical aberration and also C5, you can minimize this delocalization. So now the high-resolution phase contrast image matches the structure. That's something that you can see quite easily in a conventional microscope, and this was taken from a non-aberration corrected microscope. Okay, I'm going to skip this bit because it's far too much to talk about today. You've just got a CS corrector on this machine, right? Okay. So aberration correctors for imaging go after the objective lens. This is a image aberration corrected microscope at Argonne. It has both a CS corrector as well as a CC corrector, so it's pretty large. Okay. But it allows you to get very nice high resolution images, both at high energy and at low energy. We're going to skip this. We're going to skip this. Oh, nice. So today we talked about amplitude contrast versus phase contrast. Phase contrast really is more prominent at high magnifications. Amplitude contrast is more prominent at lower magnifications. You get more amplitude contrast there. It's easier to see it. Okay. Let's skip this. I'm going to skip a bunch of slides because a lot of these were too many things to talk about, and we're going to skip it. And we talked about that. We talked about that yesterday. We talked about that. And I'm going to skip this guy. Okay. I'm moving forward because I want to shift to a different topic. We've talked for about 45 minutes, and I want to go forward. And no, skip this. Okay, I want to go. So, all right. We've mainly been talking about TEM imaging so far. So we've had a straight through parallel beam hitting the sample and looked at electrons that were scattered off and formed images. We formed amplitude contrast image, diffraction contrast images, or phase contrast images. There is another operating mode in the instrument called scanning transmission microscopy. The difference, and we talked about this before, is instead of having a nice parallel beam, we have a focus beam. Okay. Is there a reason to go from TEM to STEM? And the answer is yes. Okay. So, are the instruments similar? Yes. Can you get an instrument that does both TEM and STEM? Today, the answer is yes. There are dedicated STEM instruments also that only do STEM. There are dedicated instruments that only do TEM. Okay. Okay. What's the difference between a TEM and a STEM? Not a lot. Okay. We both have a probe. We have lenses that focus the probe onto a sample. Right here, onto a sample. The big difference in TEM is the beam hitting the sample is mainly parallel. The beam hitting the sample in STEM is focused. Skip that. Okay. The nice thing about doing a STEM experiment is when we focus the beam down, we can have multiple detectors beyond the sample. In a normal TEM, we only look at the beam that's either coming through or one of the diffracted beams. By having an array of detectors underneath the sample, we can form multiple images simultaneously. So we can form a bright field image by looking at the beam that comes straight through and hits the center of the detector. We can also simultaneously get a dark field or an angular dark field image by looking at the signal that hits one of the outer detectors. So in the same image, in the same session, we have both a bright field image and a dark field image. Let's skip this slide for a moment. Skip that one. All right. STEM uses the double condenser system to focus the beam on the sample and also uses the double deflection coils to move the sample back and forth. So we have a focusing action by the lenses, and we also have a double deflection system, so the beam scans back and forth across the microscope, across the sample. In STEM, the scattered electrons fall onto detectors. The different in dark field TEM images are usually formed, and I showed you that, by only losing a certain fraction of the electrons. In STEM, we can collect all those diffracted electrons. And how do we do that? Let me go back. Oops. We go back because we have a detector that not only collects the electrons that go straight through, but it could be either an angular detector or a segmented detector and detect all of those electrons. So what are we doing in STEM? We're gathering more signal than we do in TEM. In TEM, we only take a small fraction of it. Now, in STEM, we can get all of that signal and then use it as appropriate. Sorry. I'm going to, let's see now. I'm going to skip this slide. All right. So, what's the advantage of doing that? In STEM, what we, again, as I said, we have a convergent beam. We have multiple detectors across it. The important thing is the different detectors measure electrons that have been scattered through different angles. Now, what did we tell you early on when we talked about diffraction? We said there's the atomic scattering factor, and higher Z materials scatter things to higher angles, lower Z materials scatter things to lower angles, okay? So the nice thing about STEM is by looking at high angle scattering, we can see high atomic number materials. By looking at lower angle scattering, we see lower Z atomic number materials. It's very easy to get atomic number contrast in this, okay? So in this case, we've got a silicon material with germanium layers in it and a little bit of hydrocarbon sitting on top of it, okay? By looking at the high angle dark field, we've got the high atomic number from the germanium. We see the silicon there, and we can even see some of the carbon contamination. And when we go out to vacuum, if we're looking at an annular signal, not the bright field signal, it'll be black. So it's a dark field image. The other advantage in doing STEM is in TEM, because we have a large parallel beam and a very large beam, we see a lot of diffraction contrast effects. When we go to a convergent beam, we smear those effects out, and we actually reduced the contrast. This is the same area in TEM, STEM, and high angle STEM, convergent beam STEM. Okay. Notice that's the same area. We can see that same precipitate, and we reduce the diffraction contrast. Why? Because we're smearing it out. We're taking a larger angle. Let's see what's next here. This is what the detector looks like. Let's not worry about that. The detectors in STEM can be various shapes and sizes. Many machines have, many instruments have what's called an annular detector. It's just a circular detector. Modern machines today have arrays of detectors down there. What's the difference? When an annular detector, we're integrating all that signal. We get a lot of signal. In an array of detectors, we can pick and choose which signal we want. The very first STEMs, actually the STEM itself was one of the very first microscopes designed. The very first high-resolution STEM was done by Albert Crew, this guy, and his company, Mike Isaacson, Dale Johnson is back there, and I've forgotten his name, at the University of Chicago back in the 60s. He did the first atomic resolution images with the scanning microscope ever. He had small atoms of uranium on a sample. That machine was a very complex device. It was a 30 kV instrument, lots of power supplies, everything manually operated back in the 60s. And unfortunately, they threw that machine in the garbage. They didn't save it. I would go there every once in a while and say, can I have the machine? No, no, we're saving it, we're saving it. And then one year I went and I said, where's the machine? Oh, we threw it out. All right, how do we get contrast in STEM? Particularly, how do we get this high angle contrast in STEM? It's mainly due to a scattering, atomic number scattering, and Rutherford scattering. Okay. In Rutherford scattering, the electrons come in, they interact with the nucleus of the material, and they're scattered through a high angle. We can show that that scattering angle is proportional, roughly, to the atomic number to a power. Okay? So as long as we're looking at angular scattering, the contrast that we're going to get is inversely proportional to the energy and directly proportional to the atomic number. You write the models, it says it's approximately 2. It's not always 2, but it's a power law dependence. So what does that mean? It means that this scattering cross-section dominates the signal. Notice there's no phase contrast in this. It's just simple atomic number scattering. What does that mean? What does that mean? That means that the images that we collect in STEM, A, the contrast doesn't reverse as we go to thicker samples. B, the contrast doesn't reverse as we change the focus. And we get very nice atomic number contrast. So here's an example of that. This is a lead, antimony, moly on titanium. Okay, so lots of atomic numbers. Okay, we've got a hole, so it's black. We've got the titanium, which is the light gray. We've got the lead, which is higher atomic number, and they're brighter. Okay, we can see a change in contrast, and we can get some nominal evaluation of what's present just by the contrast. Brighter areas in annular dark field are higher atomic numbers. Lighter areas are lower atomic numbers. Now, that's a simplification because you also get a change in contrast when it gets thicker. So really the contrast here is a function of atomic number times the thickness. Thicker samples scatter more, so they get a little bit brighter. Higher atomic number materials scatter more, so they're a little bit brighter. So it's really Z times T, and Z to a little bit of a power. Okay? Here's an example of high angle resolution STEM contrast. This is a barium titanate, calcium titanate. Okay? So you can see in this case we got strontium titanate, strontium ruthenium oxide, and then layers. Okay? Let's look at those layers. We'll blow them up. Here's an area of calcium titanate. Here's an area of barium titanate. Calcium's lower atomic number than barium. Barium is brighter, calcium is lower. They both have titanium, so we get the same signal from all of them. Let's look at something else. Let's look at some nano gold, and this is in a biological material. We have little particles of gold. Let's go forward. Okay. The structure, theoretically, of this biological material was an array of gold spheres surrounding a periodic structure. That's what we think it looks like. These guys would collapse down to a single point. There are an array of golds. This is not a high-resolution image. This is a very old image. Nowadays, we can do a lot better. Let's go forward. I'm going to skip this for a moment. This is what we can do today in a modern machine. Okay, we've got single atoms, okay, sitting on top of a ultracrystalline, nanocrystalline diamond. These are platinum atoms, high atomic number, on top of carbon. So we've got very small probes. We can see individual atoms. We can see arrays of atoms. We can see crystal structure in there, all with forming this very small probe on a material. Let's go forward. I don't want to talk about this today. with this high angle scattering, remember I told you the nice thing about it is we can form very small probes. We have atomic number contrast, and over this entire field of view, the focus isn't changing, the contrast isn't changing due to sample thickness. Atoms are always the same color because it's Rutherford scattering, not phase contrast scattering. Just examples of this, so we're going to skip forward. All right, I'm getting the point where I've got to stop talking now because my voice is going pretty bad. Let me just see what's left here. I think I want to stop right here. Yeah, we may come back to this later. Let me just see what else is here. Aberrations. Yeah, we don't have a probe corrector on this machine. It's an image corrector, so I'm going to skip these slides. Yeah, we're going to stop here, I think. Yeah, I'm just looking to see what else is here. If there's anything else we should talk about. Confocal, you don't do here. This is all confocal microscopy, so we'll not talk about that. And we're not going to talk about this. Yeah, that's a good time. I need a break. My voice is shot. Okay. So what did we talk about today? Just now, we talked about a TEM image. We talked about the type of contrast you get from a TEM image. You either have amplitude contrast, diffraction contrast, or phase contrast. If you're doing high-resolution imaging, you're doing phase contrast. In phase contrast, you have to worry about a lot of things: the thickness of the sample, the focus of the sample, the aberration coefficients of the microscope. Okay. In amplitude contrast, it's a lot simpler because we're putting an aperture around, we're blocking away diffracted beams, and we get dark and bright areas. Those dark and bright areas have to do with how the beams are diffracted off and how you set up the diffracting conditions. In STEM, we have a completely different contrast mechanism. We can get both a bright field image as well as a dark field image. The nice thing about STEM is that in contrast, in comparison to TEM, in TEM, in a high resolution image, you can get either a white atom or a black atom depending on how thick the sample is or what the focus is. In STEM, it's not the case because it's Rutherford scattering. The contrast of the image doesn't change with thickness, doesn't change with focus. It does change, it does get blurry as the sample gets thicker, but the contrast doesn't change, okay? We can form nice small probes. We can get atomic number contrast in STEM. We didn't talk about high resolution imaging in STEM. That's something else that we're just gonna skip for now, okay? I'm gonna stop now because we need to take a break. Hamish is gonna pick up and go back to TEM imaging and talk about diffraction contrast, right? I think that, or is dynamical theory first and then diffraction contrast. And I'm gonna shut up for a little while, okay? All right, let's take a break.